So we've talked previously about the exponential growth model, and today we're going to be talking about the logistic growth model. And we saw how the exponential growth model is very helpful for situations such as modeling radioactive decay. But in other situations, the logistic growth model is more helpful. For example, in population growth, it follows more of a logistic growth rather than an exponential growth. So to remind everyone what logistic functions look like, let me first review that. So we have logistic functions will take the form of y is equal to some constant m divided by 1 plus a, which is another constant, times e to the minus k over t. And let's just try to see how, or let's just try to rederive how this function behaves. And that hopefully helps get us more intuition. So let's find the y-intercept. So when t is equal to 0, we get that this term becomes 1. So y of 0 is simply m times 1 over a. And so that will be our y-intercept, m divided by 1 over 1 plus a. And now as t tends towards infinity, so limit of m over 1 plus a times e to the minus kt of t towards infinity, we know that this function with the e, the exponential function, will become closer and closer to 0. So we're multiplying a by 0 essentially, and then that means we're left over with just m divided by 1, so we get m. So as t tends towards infinity, we're seeing that we have a horizontal asymptote at y is equal to m. And as t tends towards negative infinity of the same function, now the behavior of the exponential function, which basically like trumps all the other functions, this exponential function will be e to the power of some positive, like really large positive number, and therefore our denominator will be extremely large, and so m over a large denominator will essentially be 0, like lead us towards 0. So our second horizontal asymptote is at y equals 0, which we're approaching as we go towards negative infinity. So essentially we're getting some sort of behavior that looks like this, where for really large t we're heading towards the asymptote of m, and then for small t, we're heading towards the asymptote of y equals 0. And if you think about this in the lens of modeling population growth, we can kind of think of m as the carrying capacity in that is the maximum population capacity in whatever model we have. And initially, when we're far away from this like carrying capacity, we grow really fast. But as we get closer to the carrying capacity, our rate of change of growth diminishes. And if you can kind of look at this function, this also becomes concave down at positive t. So it means that, in fact, the rate of change of our growth decreases as we increase in t. And so that kind of models how population grows, because there is a limit to the amount of population like, which is not something we would be able to model with an exponential function. Because if we had an exponential function, and let me just draw it out in the same area, an exponential function would look something like this, where we would continually keep growing, and we know that that does not seem like a valid model for large values of t. So a logistic growth model is also very helpful in other cases, such as population growth. So we've seen and reviewed what logistic functions look like. Now let's use calculus to derive the general logistic function. And so before doing that, the differential equation, so the differential equation governing logistic functions is dp. So now, like, I'm using p because I'm saying that, like, we're just going to deal with population growth. So p is going to be population. dp over dt is equal to k divided by m times p times m minus p. So m is another constant and is the only variable. So k is also a constant. That just determines like the scale of how the function looks. So it will shift and scale the logistic function, and m over here is the same carrying capacity we saw earlier. And you can kind of see if population exceeds the carrying capacity, change our change in population over time will be negative and will decrease. So that is our initial value problem. And now for the end of the video, I'm just going to derive this general logistic function over here from the differential equation. So let's derive it. So once again, the differential equation is dp over dt is equal to k over m times p times m minus p. We see that this equation is separable. This is a function of p, and then this I can treat as a function of t. So I can rewrite this as 1 over p times m minus p. 1 over p times m minus p times dp is equal to k over m times dt. I'm gonna be finding the integral of both sides. Over here, this fraction, I cannot currently manipulate it and find a closed form integral, but I can use a trick called partial fraction decomposition, and hopefully you guys remember what that is from your pre-calculus. Oh my, not partial function, partial fraction decomposition. And so let's decompose this fraction into two separate fractions, where the numerator is some x over p plus a fraction with denominator m minus p. And so the equation I would get is m times x minus p times x is equal to y, or not equal to, plus y times p is equal to 1. And to be explicit, this is equal to 1 plus 0p. And so looking at the terms with the p terms, I get minus x plus y is equal to 0. So x is equal to y. And I get m times x is equal to 1. So taking these two. And I can use this to solve for x, and x is easily 1 over m. And since x is equal to y is also 1 over m. So our new integral looks like 1 over m times p plus 1 over m times m minus p dp is equal to the integral of k over m times dt. Let's just do the right side first since it's easier. This is just k over m times t plus constant c. The left side, we can kind of see that since it's a function of p on both sides, this will be like natural log equations we get out of it. 1 over m is a constant, so the first one will be 1 over n times the natural log of absolute value of p. Over here, we also can take 1 over m as a constant. We can have natural log of m minus p. But because it's a minus p, and if you were to I'm just skipping steps, but if you were to take the derivative of this, you get 1 over m minus p times minus 1. And so to get this, to get a positive number, this has to be a negative over here. So we get that negative. And so now this is our new equality. We see that everything has a 1 over m, so why not just multiply by m? So I get ln p is minus ln m minus p is equal to k times t. And m, which is a constant, times a constant will still remain a constant, so we can just write this as plus c. Now I can rewrite this. I can rewrite this this term on the left as ln of absolute value of p divided by absolute value of m minus p. This is just through the rules of natural logarithms, and that's equal to kt plus c. Now, if you recall the exponential derivation, I can just take e to the power on both sides. So I get p divided by, or absolute value of p divided by absolute value of m minus p is equal to e to the kt plus c. And let me continue over here. So what I have right now is absolute value of p divided by absolute value of m minus p is equal to e to the power of c times e to the power of kt. Now this term is just another constant as well. So what I am left over with is absolute value of p divided by absolute value of m minus p is equal to some constant c times e to the power of kt. Now let's try to reason about this left side over here. If p is positive, since the carrying capacity will well, also it's like, since this is an absolute value, we can just get rid of it by just doing p over m minus p is equal to plus or minus c times e to the power of kt. Now this plus or minus c, that's just gonna shift the constant, and so we can again rewrite this as p is equal to some constant c times e to the power of kt times m minus p. And let me actually start this on a fresh page. So we have so far what we have derived is p is equal to some constant c times e to the power of kt times m minus p. Now we get p is equal to c times e to the power of kt m minus minus c times p e to the power of kt. Our goal is to get p isolated, so let me reshuffle this, and I get p plus c to the power c times p to the power of e t is equal to e to the power of ktm. Now that leaves us with p times 1 plus c times e to the power of kt, and hopefully now you guys can see the final form coming through. Dividing, I get p is equal to c times e to the power of kt m divided by 1 plus c to the power of e, or c times e to the power of kt. If I just divide by this term, I can rewrite this as p is equal to m divided by 1 divided by c to the power divided by 1 over c times e to the kt plus, I'm just like, this divided by this term will just be 1, and that's just if I can rewrite that, that's just the same thing as c, or 1 divided by c is just another constant, so I'll just keep it at c, but 1 divided by e times e to the power of kt is just e to the power of minus kt plus 1. And notice how this is the same thing as 1 plus 1 over a times e to the power minus kt, since a is a constant and m is the same carrying capacity we started with. So we have finally derived the logistic function from the original differential equation. And I think the key step that we did was that partial fraction decomposition to be able to take the integral, and how we also divided by c times e to the kt to get it into the form that we were looking for. And notice how every time I did some manipulation on the constant, I just kept rewriting it as c, because I don't care what the value of the constant is. I just want it to stand for the fact that it is a constant. So hopefully the derivation of the logistic growth was satisfying and informative.